Okay, now. Okay, we're
Oh,
on.
wow. Okay.
Cool.
Not bad.
Okay.
Um,
Okay.
all
Awesome.
right.
Very well.
I'm.
Yeah. So thank you so
I
much,
hope.
Marius. Yeah. I think you
Yeah,
could go ahead. Yeah. Cool.
yeah. I hope you can see my screen. If not, scream at me. Um, as I already said, my name is Marius. I work in the Go Ethereum team, and today we are talking about deciphering Pectra and Fusaka. And some some of the slides are old slides. That's why the title is wrong. But yeah, we're going to talk a bit about the next hard fork, or the coming hard fork, and the hard fork afterwards. And Pectra kind of is the biggest upgrade that we probably ever had. Has 11 EIPs in total, 4 on the consensus layer, 5 on the execution layer, and 2 kind of between the layers. And you usually for the hard forks you have meta EIPs, and these contain the hard fork, basically what the hard fork contains, a list of all the EIPs that the hard fork contains. And you can see here the meta EIP for Pectra is 7,600, and within 7,600 you have this list of EIPs that are in Pectra. And I wanted to go through some of the EIPs. By the way, if you have questions, I cannot see the
Yeah. If you have questions, meanwhile, feel free to raise your hand or write to the comments, and I will let you know, Marius.
Perfect, exactly. Yeah, so we have, I kind of categorized these EIPs into like minor and then execution layer and consensus layer EIPs, just to put them in a bit of perspective. We have 7549, which is an EIP on the consensus layer, which moves the committee index out of the attestation. And that's a change that will allow you to, or the consensus layer to combine attestations better, because you can take different attestations from different sync committees. I don't know. I'm not an expert on the consensus layer, but what it will do, it will reduce the number of pairings needed to verify a block quite significantly, and this benefits ZK proofs that prove the CL block. There aren't many ZK circuits currently around that prove CL blocks, but hopefully in the future, especially with this like new idea of the beam chain, this will be something that is probably going to happen at some point, that we are ZK proving CL blocks. Another benefit that this has is, or another change that this has, is it removes the number of attestations that are in that you can put into a block, and they were removed quite significant. They were reduced quite significantly from 256 to 8. And I don't know. I personally think 8 is kind of a bit too low. But yeah, time will tell if we are going to increase that in the next hard fork. The problem that we've seen with these 8 attestations per block, or per slot, is that when we have very little blocks being produced, for example on Holeshki, we had this problem that we couldn't include enough attestations into the block, because we could only include 8, like attestation aggregates. So those are not like single attestations; those are aggregates of the attestations. But we could only put 8, and that means if you only have like, I don't know, like 5 or 10 blocks in an epoch, because there are very few nodes actually producing blocks, then the amount of attestations that you can put in this is kind of small. So the network deteriorates even more, and it might lead to loss of finalization, even if enough nodes are online, only because you cannot put all of their votes into the blocks, basically. So yeah, this is 7549. 7840, add blob schedule to the execution layer. We previously had the number hard-coded to 36, which means on average, like the blob mechanism uses 1559 mechanism. Basically, you have a target and you have a maximum, and whenever the number of blobs in the block is greater than the target, so if you put more than 3 blobs in a block, then the fee will rise. And if the number of blobs in a block is less than the target, then the fee will decrease. And so, yeah, this PR allows the EL to specify how many blocks can be put in a block. Previously, as I said, this was hard coded. It's not really. It's more like a like a tiny change. It's not really important. But sometimes we bundle these changes with hard forks that are not technically part of the consensus, just because the hard fork gives us a great chilling point, like a point where all of the nodes on the network have to update, so we can put in stuff that is not absolutely necessary for everyone to update to, but it's very nice if everyone would update to it. And then we have 7691, which is the blob increase. And in this EIP, we increased the amount of blobs per block from target of 3, maximum of 6, to target of 6, maximum of 9, which allows for more L2 transactions. So basically, we increase the amount of blobs that can be put in a block on average by 2 times, and the maximum just only goes up from 6 to 9, which is in order to be sure that people are not spamming the network with blobs while the blob fee is low, and shutting down nodes or nodes running out of bandwidth, all of these things. And then we have some execution layer EIPs. EIP 2537, which are the BLS precompiles. We use BLS on the consensus layer for signatures. And this EIP, you can always see based on the number how old the EIPs are. So for example, like here, all of these EIPs are in the 7000s. And you can see the 2537 is in the 2000s. So this EIP is like 5 or 6 years old at this point. And it was postponed. It was scheduled a few times. It was scheduled even before the merge, I think. But it was postponed multiple times because there were questions around whether we can do what this EIP does in a different way with EVM Max, for example. I think EVM Max was called differently back then. But basically, if we have good big number support in the EVM, then we could have we could have thought about implementing these precompiles just as smart contracts. But yeah, in the meantime, we launched the beacon chain. The beacon chain runs on. Okay, that's extremely loud. The beacon chain runs on BLS, and so we need a way that it's just normal that we need a way to verify BLS signatures in the EVM. But this is not only for the for signature verification, but there are actually like 6 or 7 precompiles added with this, and or even more, and they can be used to do other stuff on the BLS curve, and that's pretty cool because you can, for example, a few snarks, I think, ZK snarks are built on the BLS curve, and and that means some of the ZK L2s can also use this instead of a smart contract for the BLS verification on mainnet. Then we have EIP 2935, the block hashes. Kind of, if you think about Ethereum, if you think about the execution layer, you can think about it as a state transition function. Like you have a pre-state, and then you have a transaction, and this transaction gets applied, and then you have a post-state. And the problem right now was that this function wasn't pure, because you needed, like in the EVM, there's the block hash opcode, which gives you access to the last 256 block hashes. And in order to do that, we need, in order to execute a transaction, not only the pre-state, but we also need the last 256 block hashes. And that's kind of a pain, because that means in order to verify a transaction, you need to have access to the pre-state and the header chain, and the current header, and the previous header. And like the current header and the previous header, just for computing the 1559 values, but you also need the last 200, at least the last 256 headers. And that's kind of ugly, and it's not great for proving. Again, doing CK proofs over this. And this EIP kind of puts the block hashes from this kind of extra thing that you need to maintain into the EVM. And because it's now, these block hashes are now stored into the state. And because the block hashes are now stored in the state, we can actually extend it. We can put more. And so we decided to extend it to 8,191 hashes. And with this, the state transition function is, at least in theory, pure, which is quite nice. And then we have EIP 7623, the call data cost. And this EIP kind of increases the call data, the cost for call data. So call data is the data that you are sending in your transaction to a smart contract. And this call data was used, for example, by L2s before 4844 in order to post data onto L1. But the problem with this is that there are two problems. It kind of blows up the history. So call data is not, like, is only available during that transaction in the EVM. Afterwards, it gets kind of forgotten from the point of the, like, it's not stored in the state, but it's part of the history. And so that means that during this initial phase of L2's ramping up, the amount of history that the nodes had to store increased kind of exponentially. And what this call data cost increase does is it increases the amount that call data costs, but in a very interesting way, so that most of the transactions are actually not going to be more expensive. Most of the use cases are not going to be more expensive. Only if you have very little execution and a lot of data, then you are going to feel the cost increase. But if you have, like most of the transactions, you put some data in, some call data, and then they're doing a bunch of execution, and then they're storing something or doing a swap or whatever. So there's very little call data compared to the amount of execution that you're doing. And in this case, this increase will not affect you at all. Yes, but it also reduces the worst case block from 7 megabyte to 2.8 megabyte. And that is also something that we need to think about now that we have these big blob transactions in every block. We need to kind of think about how big are our blocks going to be. And the size of the block is directly tied to the gas limit. So the gas limit kind of gives you the upper size of what a block can be in the worst case. And if we want to increase the gas limit, we would also directly increase the worst case block. And that would mean that we could see like 10 megabyte blocks or something. And if you think about it, if you have like a 10 megabyte connection and you get a 10 megabyte block, then you need already 1 second just to download the block. And then you also need to send the block to your peers, and you might have only like a 5 megabyte upload. That means in order to send the block to one peer, you would need 2 seconds, and you're usually sending the block to like a logarithmic amount of the number of your peers. So usually like 6 or 7 peers. So yeah, this is kind of what we always have to balance. Is like the worst case when we think about stuff. All right. Now ELCL EIPs. We have EIP 7685 EL requests. Basically, this introduces a new mechanism for the EL to notify the CL of events. So we have the engine API is basically the mechanism for the CL to tell the EL what to do. And these requests, they give the EL kind of a mechanism to notify back the CL about stuff that is happening on EL. Then we have 6110, 61110, which is deposits on chain. Previously, the CL nodes would just listen to the events on the deposit contract. So if someone deposits, the CL would listen for events on this one contract. The contract would emit an event, and then the CL would know, okay, there's someone just deposited into the deposit contract. But for that to work, you would need logs to work. So the CL nodes would continuously scan the logs of the EL, which is a very brittle mechanism, and it's also not great performance-wise. So with this is both an increase in performance, and it makes the whole thing less brittle, and we can way quicker include deposits on chain. And then we have 7002, which is execution layer triggered withdrawals. this EIP allows for smart contracts to trigger exits on the beacon chain. Basically, before you would need to send a message on the consensus layer to trigger an exit, and now you can do that on the execution layer. And this allows for building trustless, there's an S missing, trustless staking pools, where you can stake into a contract, and if you don't want to stake anymore, this contract can trigger the unstaking mechanism, and you will get your money back. And there's not no central entity involved instead of the operator that you have to trust, but that's another story. And then we have a couple of bigger features in Pectra. We have 7251 max EB, which increases the staking limit from 32 ETH to 2048. And it also allows for consolidation, which means you can take multiple validators. So in Ethereum, previously you could only stake in multiples of 32. And so we have a lot of active validators, 1 million active validators, but way less nodes because you can run multiple validators on one node. But you can also now consolidate them, and that means you have way less networking overhead. You have way less cost for running your hardware. And MaxEB also allows for automatically compounding stake. Previously, you would need to wait until you have another 32 ETH in order to create a new validator, and now your validators become auto compounding. And if everyone would take advantage of these consolidations, we could see the number of active validators go from 1 million down to 17,000. In theory, I don't think that's very. I don't think that's going to happen. I think that's very unlikely that we will see everyone consolidating their stuff, but I hope at least we will not see an increase in active validators, which would be really nice, because active validators means like all of these validators have to sign attestations. All of these validators have to send these attestations over the network, aggregate the attestations. There's a lot of work that needs to be done for this network to work. And basically, if you think about it, at some point your node needs to hear from all of the active validators. So every node will get, at least in some way, a message from 1 million other entities. And so that's it doesn't scale that well. And we are currently like very close to this limit where it just doesn't work anymore, where it becomes kind of brittle. And so, hopefully a lot of these bigger operators will take advantage of this consolidation feature. And then we have EIP 7702, set EOA code. Basically, we have this idea of account abstraction, which means that you're not really, you're using basically a smart account or smart wallet, or basically a smart contract as your wallet. But it's very hard. It turns out it's very hard to get people to switch over to these smart contract wallets with their accounts. And so one way of doing it is allowing your external owned account to act as if it was a smart contract. And that is what 7702 does. It allows, and this is kind of cool. Basically, your EOA is now both an EOA and a smart contract. So it has some code, so it can do interesting things. For example, it can do batching. So I don't know, probably most of you are aware, but in ERC20, the token standard, you have to send, in order to send a transaction to a contract, you have to do two transactions. You have to first approve this ERC20 contract, and then you have to transfer from. And this is something that you can do now in these EOA, in your EOA with these 7702 contracts within one transaction, which is nicer. It also allows for sponsorship. So basically someone else is paying for your gas, or you can pay, you can send an ERC20 token and someone else is paying for your gas, or and they get refunded with this ERC20 token. So you don't really need to own any ETH to interact with Ethereum. And it also allows for something called privileged de-escalation. So you can sign subkeys that only access a percentage of funds, or you can say, okay, this key is on my hot wallet, so it can only transfer, I don't know, $100 every day. And this other key is my meme coin key, so it can only transfer meme coins, and so on. So those are all of the features of Pectra. When is it going to happen? It's scheduled for May the 7th, but it's already live on Hoodie, Sepolia, Holeshki, and Ephemery. So if you want to check it out, you can do so on the testnets. And there's also like a bug bounty happening right now. So you can also like try to get the bug bounty. Oh yeah. Yes. I don't know. Are there any questions yet about Pectra?
Let's maybe take a minute to see if there are any questions. We got almost 40 people, so there might be some. Yeah, folks, if you have any thoughts, any questions, feel free to raise your hand, write in the chat. Joshi, yeah.
Yeah, hello. I wanted to ask a little bit about the 6110 deposits on chain. So I understood the old mechanism that you described, where CL nodes basically scrape the EL logs and watch for contract events. And I understand why that's not efficient. It sounds clunky and clumsy, but I'm not really clear on what the new thing that they're going to do is. Could you briefly describe that?
Yes. So basically, the EL node. Let me go. You guys can still see my screen, right?
Yeah, we see your editor now.
Yeah. Where is it? So basically, after you execute the consensus MISC, no. I'm not really sure where they put it. Basically, after you execute the transaction, after you execute the block, you will collect all of the past deposit logs. After you execute, so this is the code. I don't know if it's too small, but this is basically the code within Geth where you execute a transaction. You just iterate over all of the transactions, you execute them in the EVM, and you collect all of the receipts and all of the logs. And afterwards, now in Prague, here you can see it, you have these 6110, 7002, and 7251. And basically for those, you just take all of the, for 6110, you pass the deposit logs. So we go through all of the logs and see, are they coming from the deposit contracts? contract, and if they're coming from the deposit contract, we make sure that they are from the right topic, because that is actually one of the problems that happened on Holeshki. No, was it? No, it was Sepolia. On Sepolia, the deposit contract is token gated. That means the deposit contract itself is an ERC20 token. And whenever you deposit into this ERC20 token or into this deposit contract, it will emit two events. It will emit the deposited event, and it will emit an ERC20 transfer event. And the problem was that this code here would just error out because we're not able to pass this ERC20 transfer event. And so we would not be able to create a block with those events in it, which was bad. So there weren't any blocks created, because basically we would create the block, we would fill it up with transactions, and at the end we would do the same step here, pass the deposit logs, and then that would error, and we would just not produce any blocks. So all of the blocks on Sepolia would be empty. Yeah, this is kind of how the mechanism works. Basically, you go through all of the logs that we have, and you put them into these requests, and the requests are part of the block and are returned to the CL.
Okay, so that makes sense, basically. So it sounds like in the old days, the CL nodes would basically act just like any other DApp front end and read the logs the old school way. Now we're shifting that burden of looking through the logs and finding the relevant deposit ones over to the EL itself, and then the result is that like that data is part of the block now. Is that right?
Yes, exactly.
And so then
it's kind of better because previously we would need to, like, you would do it via RPC with the get logs, and you would need to go through all of the logs and filter them. And here we have the logs available because we just produced them, and so we don't need to pull them up from the database again and all of these things.
I see. So there's still this function you're showing here is running on logs that are like freshly generated in memory because we just built this block. So it's like pretty efficient. Is that the idea?
Exactly.
Okay, cool. Yeah, I was wondering because I'm thinking it is actually more like on-chain computation on the EL, I guess, right? But is it just not a lot more? It's like negligible or not something?
It's very, yeah. This is okay. This is very, very quick.
Thank you for showing me. That makes a lot of sense.
Yeah, very well. Thank you so much for elaborating on that. We have some more hands up here. Samarat, if you have a question.
So I wanted to ask, like you said that the number of validators won't go down that much because they won't consolidate their hardware. But why would that be if they are incentivized? Like the hardware requirements would decrease.
Yes, but I think there's a tiny bit of risk, right? If you get slashed on 32 ETH, you get slashed on 32 ETH. But if you get if you have like 10 validators and you get slashed on one of them, you're only losing 32 ETH at maximum. You won't lose that much. But if you get slashed on the consolidated, like 320 ETH, you will get slashed much more. I think some of the people are thinking this way, is that this consolidation, there is an incentive to do it, but I like from what I kind of know about the Ethereum stakers, most of them are kind of timid when it comes to these kind of things. They don't really want to change their setups. And they are also lazy, and they just don't do it because if they, like, you can run multiple keys on one machine, right? So you can run roughly, I don't know, 1,000 keys on a machine. So there's not that yes, your machine might run a bit cooler, but there's not that much of an incentive to consolidate.
Very well. We have one more question from Shane.
Yeah, just about the set EOA accounts, EIP 7702. Trying to understand how to think about it. So if you are an externally owned account and you now have set a code that allows you to point at another smart contract to execute code, is it that like the code property of the EOA now has some pointer to that other smart contract? And if you now send a transaction to your EOA, then it's going to just auto execute whatever smart contract it's pointing to. And do you now lose your like privileges to just do like the easy transfer? Is it always call this other smart contract every time you just try to hit your EOA?
So you like really correctly described the mechanism. Basically, we put into your EOA. We put this the 0xEF and then the contract address that you're pointing to. And this is like where you're delegating to. And then you can remove your delegation by sending a transaction. Well, no, I think that was changed. That might have been changed at some point. I think you can set the nonce of your delegation so that it can time out at some point if you're sending another transaction or a few other transactions. Because you might want to send a transaction from your EOA without the delegation going away.
Got it.
It's this I don't know. It's the EOF stuff. Sorry, the AA stuff. I'm not super deep into that.
Yeah, it seems like you would want to switch smart contracts that your EOA is pointing to at some frequency, and I don't know if that takes additional transactions or if you could do, say, one transaction that sets the code to the new smart contract and then executes it all in one, and then if you want to switch to another smart contract that you're pointing to, same thing, just like send another update to the code and then into the code property to get a new pointer, and then it'll execute it automatically. Just trying to think about how to save gas for multiple transactions. That's kind of most of the point.
Yeah, exactly. Exactly. This is the code that resolves the delegation. Basically, we are looking up the code on the address where you're sending to, and if it's before Prague, then we're just returning the code, and afterwards we're calling this pass delegation function, which will take the code, and it needs this delegation EF 0100 prefix, and afterwards it has the address that you're delegating to, and so you will just return the code of the target where your contract is pointing to, basically. But if you if you are pointing to a contract that is pointing to another contract, then we will not resolve the second delegation.
Okay. Not nested.
Okay, we have one more question from Justin. If you can make it quick, Justin, if you have a question.
Hello?
Yes,
Please,
go ahead.
could you move your slide 3 steps back? I want to ask a question from there.
This one?
The next one. Yes. All right. On EIP 6110 deposits on chain. Okay, so previously CL nodes would listen to events from deposit contract. Now that happens automatically. Please, could you throw light, the mechanism? I don't understand the automatic approach.
Yeah,
Because
basically, I already showed that a bit ago. This is what we did here with in the state processor. Previously, you would execute the block, and during the block execution, we save all of the receipts, and then this other node would ask us for the receipts. Give me the receipts of the last block. And then it would go through the receipts at this block and see, okay, there was a deposit to this event, there was a deposit to the deposit contract, and we're going to take this deposit and put it into the queue. And now we're doing this used to be done by the consensus layer, and now it's done by the execution layer. After the block is processed, we will go through, as I said here, we will go through all of the logs and see if there's any that are coming from the deposit contract with this deposit topic, which would say someone deposited, and then we will add them to the requests, and these requests are now part of the block, and they are returned to the consensus layer. So the consensus layer will get a list of all of these events that happened from the execution layer directly when it also gets the block. And previously, it would need to ask for all of the logs. All of the logs would be returned, and then it would do the filtering, and this was kind of horrible.
all right, thank you.
Okay, thank you guys. Let's move on for now. Let's jump into Fusaka, and we can take some more questions after.
Cool. Let me quickly get. I need to charge my laptop. Okay, Fusaka. Fusaka is a combination of Fulu and Osaka. Pectra is the combination of Prague and Electra. Basically, we have two different naming schemes. I don't know if you guys know, but on the execution layer, we use cities where DEFCON has happened. And on the consensus layer, we use the name of stars. And on the consensus layer, the stars are alphabetical. And on the execution layer, the cities are just by like when DEFCON has happened. And so after DEFCON Prague, we had DEFCON Osaka. And Osaka has a few goals. It aims to give more scale to blobs with PIRDAS. It aims to improve the EBM with EOF. And it might contain some smaller EIPs, but the discussions for that have not concluded yet. But it also might act as a shelling point for other EIPs. As I said, we typically have EIPs that are consensus critical, so every node needs to update at exactly the same time, and that those need to go into hard forks. But there are also EIPs where it's kind of nice if everyone updates at a similar time. And these EIPs, they get sometimes bundled into a hard fork in order just to make sure that everyone implements it by that time. And so the EIPs that the Fusaka is hopefully like this kind of shelling point is EIP 4444 or 44s, which is history expiry. Basically, you don't really need, as a node, you don't really need the old history. You need the header chain, and you need the current state, but you don't need all of the old transactions. The old transactions are only really needed for syncing a full node, but you could also get them from somewhere else. And so EIP 4.4 is about not requiring every node on the network to have these old transactions. Then we have EIP 7642, which is ETH69. Basically, they made this great decision back in the day to call the networking protocol of Ethereum ETH. So all lowercase ETH and then slash a number. That is usually the networking protocol. And we're currently using ETH68. And the next one is ETH69. And ETH69 removes a lot of pre-merge fields. Yeah, I don't know. I'm one of the authors of ETH69, so I don't want to get too deep into it, but it's going to be a cool improvement. And then we have EIP 7892, which are the BPO only forks, or block, and BPO stands for blob parameters only. So I will talk about this later. But we have, usually we think about these forks as having some headliner, some feature that we really want to ship, and other features that could also fit into this. And one of the headliners for Fusaka is definitely PDAS. DAS stands for data availability sampling. I don't know if you guys heard about how 4844 works in this study session yet, but basically we send these transactions that have a lot of data with them, but this data can be forgotten after a month. But now the problem is that everyone has to download all of this data, keep it for a month, and then they can forget it. But it's not really needed to be like that everyone downloads everything. What we can do is something called data availability sampling, where everyone who's an honest actor in the network downloads some parts that they randomly choose. And if sufficient enough people do this, we know that with high probability, the data wasn't withheld. So the data was actually published. And that is what data availability is all about, is that you need to guarantee that the data was published. And otherwise, that's the only thing that L2s can actually do, is just withhold the data and not publish the data. Yeah. So it's this is the security mechanisms for L2s. PDAS is a one-dimensional erasure encoding. Basically, we take the blob data and we extend it and erasure encode it, and then we take 128 proofs called cell proofs and send them, and send some pieces of data on different columns. Basically, you have different subnets in the consensus layer networking. Subnets basically means one topic. So in this topic, you just send all of the columns from the first column you send to this subnet, the second column you send to this subnet, as you can see on the right, on the picture on the right. And now the consensus layer nodes will need to subscribe to some of these subnets, and you can decide based on your bandwidth if you want to describe to 10 subnets or 20 or all of them. And we expect people that have a lot of stake, that have a lot of bandwidth, that are not home stakers, to subscribe to just all of them and make sure all of the data is available anyway. Yeah, there are changes both on the EL and on the CL. On the EL, the changes are kind of easy. You need to implement this new blobs v2 wrapper, which is basically the new way of proving these erasure encoded blobs, and you need to have this get blobs v2 engine API endpoint and a bunch of like smaller things. And on the CL, they need to now subscribe to the multiple subnets and verify random portions of this erasure encoded blob data. And so this is basically the second step. 4844 was the first step. PRDAS is the second step. And the third step is full DAS with two-dimensional erasure encoded data. Yes. The next the next big feature in currently slated for Fusaka is EOF. It introduces a newer, more structure into EVM bytecode, basically. It introduces a header format that is similar to ELF, and it defines code and data sections. Right now, EVM contracts have the data and the code in the same section, which is for security purposes. It's not super great because you cannot prove that that the contract was correctly done, and EOF also introduces a bunch of new checks, and these checks they happen at compile time. Basically, you make sure that the contract works as expected when you sorry, not at compile time, at deploy time, when you deploy the contract. So right now you can create a contract and deploy it that just has a jump that jumps into like after the contract into nothingness, and then the EVM will just stop and return an error and that the transaction failed. But with EOF, these checks will be done at the deploy time, which means you don't need to do this analysis whether a jump lands in some data section or lands after the contract at runtime. And so this kind of means that we could remove some of the checks from the EVM because they will all be done, or at least from the EOF EVM, because they will all be done when the contract is deployed. And another thing that EOF also does is it removes the dynamic jumps because they are not really needed, but they are kind of a pain in the ass to work with. So for static analyzers, you kind of want only to have static jumps. It adds some opcodes and it removes gas and code observability. Right now you have the gas opcode, which tells you how much gas you currently still have left. And there's a bunch of other opcodes that kind of depend on how much gas you have left, like that kind of lets you interact with the amount of gas that you are sending to somewhere. So if you're doing a call, if you're calling from one contract into another contract, then you can specify how much gas you want to give to this call. And all of this is kind of gas observability. So if we would ever change the gas cost of something, it's kind of hard to do because we need to think about like how are people using this, and are they only like sending X amount of gas to this contract under the assumption that it will just work, and all of these things. And the other thing is code observability. Basically, one contract can observe the code of another, and that is not. It's not really bad, but it's also not great because we could think about ideas of just modifying contracts, and that wouldn't work if we have code observability. But I don't think we will ever create a way of like modifying contracts anyway. So it's a nice, neat feature, but it's not really needed. And EOF also improves the proving efficiency of CK proofs over EVM contracts because you remove a lot of checks from the runtime. So basically, when a CK proof, if you want to like do a CK proof over the execution of a EVM contract, for every opcode, you need to prove that it doesn't underflow the stack, it doesn't overflow the stack, and a bunch of other things. But because these things are all checked during the deploy time, you don't need to check them during the execution, and that means that that CK proofs are much faster and need less time to prove and less space. And then we have some minor EIPs that might or might not make it into Fusaka. As I said, BPO, the blob parameter only EIP, that is basically a new mechanism to do forks that only change the blob parameter, which allows increasing the blob throughput quickly. I think that is just an artifact on how the CL teams kind of structured their code, because when they want to implement a new fork, hard fork, they are duplicating a lot of their code. And now they don't want to do this for like these minor hard forks that only change one parameter, basically, or two parameters. And so this is a way for them to kind of make a hard fork that is not really a hard fork, so that they don't have to copy these hundreds and hundreds of files. But I don't know. I think they should. My opinion is that they should just fix the software and not do this weird forking thing, but like implement their software in a proper way so that they don't need to do this every time we do a hard fork. Anyway, EIP 7823, it's an upper bound for the modx precompile. And there's another one that is like repricing the modx precompile. Basically, the modx precompile is one of the worst precompiles that we have. It just does modx, modular exponentiation, x to the power of y modulo p. And the problem with this is I think I've seen like 5 or 6 consensus bugs with this already. Every new client kind of has a bug there. They're making some things wrong. with this very, very easy precompile. Like, it's not a complicated thing. But also, for example, we found a bug in the Golang standard library because of this. Because it turned out that, like, it's unbounded. You can just put very, very big numbers in, as much as the gas limit lets you. And so someone found out, Guido, like one of the great security guys, found out that if you put in a really, really big number with an even modulus, then the thing takes ages. And so I went into the standard library and looked, like, we were using the Go standard library implementation of this, and looked in and what was happening. And they were using a different algorithm for even modulus and odd modulus. And if you know a bit about cryptography, in cryptography, basically everything is the modulus is usually a prime, and the prime is always odd. So everyone that was testing it with an odd modulus, because that's just like, we didn't even think about using the ModX precompile with an even modulus. But it turns out if you have like an even modulus that is 6,000 digits long, then it would use this other algorithm, which was really, really slow. So we implemented a new algorithm for the standard library, and that fixed it. But anyway, the ModX precompile is still one of the things that is kind of holding us back from increasing the gas limit, because it's just a bit underpriced and it's unbounded. And so we need to address this edge case of like putting in, like, no one needs the ModX precompile with a 6,000 byte long modulus. That's just not needed. Like, in no cryptography is this needed. So we are just going to hopefully limit this at some point. And the other one is RIP 7212. And you can see that this is an RIP, not an EIP. EIP are Ethereum improvement proposals, and RIP are rollup improvement proposals. So this RIP was first implemented on rollups. And it adds a precompile to verify SecP 256R1 signatures. In Ethereum, we use SecP 256K1, which was the original signature scheme. And NIST kind of changed it, or productionized it, standardized the R1 version. And this is also supported in all of the hardware secure elements. So this would allow us to do smart contract wallets where the keys are in your phone's secure element, so it cannot be extracted. And it's really, really cool. And I hope it will go onto mainnet. It will go onto mainnet at some point, but we don't know if it's going to be in Fusaka or in the hard fork afterwards. That's it. Thank you very much for listening to me. I'm open to all questions about Fusaka, about anything else in Ethereum. And go ahead.
Lovely. Thank you so much, Marius. Amazing. Very well. It was a really great insight. And please ask questions. Please raise your hand. And we have some questions in the comments, but because of the Jitsi bugs, we cannot really read them. So if you want to read out loud a question that you shared before, please do so. Please raise your hand and go ahead and ask. Hey, Moses, go ahead.
Hello. Thank you, Marius, for that presentation. This isn't technical, but I'm more political. The EOF update has been subject to like a lot of controversies with many diverging opinions. People complaining about the complexity. People saying that some of the included EAPs are not necessary. I'd just like to get your thoughts on what you think about the EOF updates in general.
Yes, that's a great question, because I also wrote a long blog post about the potential dangers and the potential downsides of EOF. So I was a skeptic for a very long time. I'm at this point where I don't really want to argue anymore. I think it's fine either way. The EOF, yes, it will add a bunch of complexity, but it's still manageable. It's not too bad. We have tested it quite well already, and it's not even like we don't even have the final version yet, but it's there's a lot of test cases for it. And I think the one argument that like kind of I wouldn't say like didn't really like fully convince me, but it made it like easier to accept, was that if we were to implement the EVM right now, it would probably look from scratch. It would probably look a lot like EOF is. So yeah, I think that was the argument where I was like, maybe we should provide this, because most languages and most L2 teams would like to have this. And so yeah, that was kind of, I'm at this point where I'm like, I don't really want to be involved in the discussions anymore. I'm fine with shipping it. I'm also fine with not shipping it. I just don't think at this point that the discussions are very productive. Like the Epsilon team that like proposes EOF is also part of the EF. They are kind of, I think they're kind of tinkering too much with the specification, where like they're adding or removing features based on a whim, based on like what makes it more likely for it to go through. And I don't like that. I think it should just be the best version that we can ship right now, and not really think about these. Think about these features in like, are they useful or are they not useful, and not is it like is it politically better to add this feature or to remove a certain feature. So yeah, I think it's fine either way. But a lot of people have stronger opinions about this than I do at this point. But it's a great question.
Yeah, it was a tough question. Yeah, thank you. But yeah, feel free to ask anything else, any other spicy questions or anything technical about the upcoming forks or yeah, Sam.
You can also ask me non-technical stuff, by the way, if you want.
Yeah. Thank you, Marius. Yeah. So yeah, I have noticed some RIPs basically on which is coming on a CCP 256 R1. And we know that ACCP 256 K1 and R1 like have some vulnerabilities in the context of quantum computing.
Yes.
And it looks, once quantum computers become practical, I think it would require reworking quite a bit of the existing infrastructure of Ethereum itself or Geth itself.
Yes.
Yeah, in your opinion, how do you see like Git and the Ethereum ecosystem preparing for the transition towards quantum resistant cryptography?
Yes, that's also a great question. So I at some point I implemented, or like I wrote an EIP about adding BLS signatures to Ethereum, to Ethereum in order to sign transactions. And this was like really, it wasn't really like a really useful EIP, but it was a nice idea. And BLS signatures are also not quantum secure or quantum proof or quantum resistant. So we need to change. So basically, we need to change two big things. We need to change how the transactions are signed on Ethereum, and we need to change how the transactions are signed on the consensus, how the consensus layer works. And then we also need to change how we're proving the blobs, because KZG is also not secure, quantum resistant. The trie itself is actually quantum resistant, but if we're moving to Verkle, which would be not quantum resistant, we would also need to move the trie to another quantum resistant scheme. So basically, there's like 4 or 5 places where we need to change. We're currently we're currently working on writing an EIP, and I also already wrote an implementation of using Falcon signatures. Basically, what I noticed during the EIP that I wrote like a year ago is that it's really easy to add a new way of signing transactions to Ethereum, because like it's impossible to sign to create a new smart contract with this new a new public key with this new new signature algorithm that matches an existing public key, because otherwise one of the signature schemes would be broken. And so what you can do is just basically add a new transaction type with this new signature scheme. And so we have an EIP proposed. I don't know if it's proposed yet, but we think we're in the process of proposing it, and an implementation to add the Falcon signatures to Ethereum. And this would be basically one of the first steps to make Ethereum quantum resistant. And then, of course, if we're adding the transaction type that is signed by Falcon, we would also need to add Falcon verification into the EVM. So if this is the problem with these post-quantum signature schemes, is they are not very well understood yet, and so they kind of need a bit more time to develop and to be standardized properly and to be understood properly, because they're based on very different assumptions than our current signatures. So yeah, it takes some time, but we are already working on it.
Thank you, Marius. Yeah, thank you.
Thank you so much. Any other questions? Any more thoughts? We have maybe a couple more minutes. Maybe one more question, anyone? And yeah, feel free to be non-technical as well. Shane, yeah.
Hey, Marius, one of the aspects of the study group is the potential to do a project for Ethereum for, say, 5 months. And I'm curious if you were to select your own project, would you think you would want to do something that's Fusaka, or is that a bit short? Because I think that's more maybe 8 months out, or maybe something more Amsterdam related. Just curious how to think about timelines for these types of things. You don't want to block teams by building this kind of like side project, for example, but also do something meaningful.
Yeah, exactly. So I think like what would be nice to have is like there's usually when you build out these new hard forks, there's usually a few tools that you kind of need. For example, for Fusaka, it would be really nice to have like a networking tool that like has an overview of where are all the shards and like how is the block propagation going. And we kind of have these tools already, or they're being developed for Fusaka. So I think, and these tools are usually like quite nice. Nice tasks for the EPF. What's the normal program or whatever, the 6-month program, because they're kind of like a task in itself, and then you learn a lot about this upgrade. So yeah, I would suggest working on Glamsterdam or Amsterdam, because there's a lot of unknowns there still. For Fusaka, we kind of know the potential EIPs that are coming in. I have an implementation for most of them. I have an implementation both for PIRDAS and for EOF. So those are kind of already covered, and I think most clients have covered them. But for the next one, for Amsterdam, it like there needs to be a lot of work done in this more exploratory phase of like, yeah, you have an EIP, and researchers are, as you will notice, great at coming up with EIPs, but they usually miss a lot of the like real world constraints that we have sometimes. So yeah, it would be nice if those researchers could have a helping hand from the EPF that are working on these on getting their ideas that they might have already proposed or looking to propose soon into a more realistic and workable state. And often during implementation or during like building tooling for them, you will find out that like maybe something about them feels a bit off, and maybe you would structure them a bit differently, or you would do the interface a bit differently, or whatever. So yeah.
Yeah, Barnaby had a call, I think last week or the week before, where it was kind of about scaling Ethereum and future research. And just at the end, he had a slide about what Amsterdam could entail, and it included like block level access list, which in my understanding, I think would just be that you have the block level, you can tell what are the like accounts that are going to be touched or like upfront, and then the EVM could probably do some optimizations, like before actually having to execute. And I'm curious if that would maybe lead to like something like parallelization. So if you know upfront that say like in one block, 2 accounts aren't going to be touched, then you could potentially run those in parallel.
Yeah. I'm not a big fan of these block level access lists. I think they are okay, but I think in general the researchers have a very optimistic view of how much this will improve things, and my view is a bit more, and not to say a lot more pessimistic than theirs. Like I think they're kind of like they're thinking about like orders of magnitude, and the way I see it, it will be like maybe 30% improvement, maybe 50% improvement, and this is like that's not a lot. This is not like this will not bring like the big like L1 throughput that we want. I think there are some other things that are way more promising on that front, like delayed state execution, delayed state root computation. But even that is like delayed execution. Delayed state root computation itself is probably also nothing. I think that delayed state root, the delayed execution is something that will probably bring significant benefits in throughput on the L1.
Okay, folks. We have another couple of minutes maybe for one last question. If anyone has any thoughts, we had some great questions here, so we can keep it going for a few minutes. Yeah.
Hi,
Yeah. Hey.
this is Kenneth. I just landed in Singapore.
Oh, nice.
Nice. Back from the ETH Taipei as well as the Web3 Festival in Hong Kong. So I have one question. I have it might be out of the topic, but I just like to ask. In a hackathon, I tried to make a centralized database for the different mempool transactions, and my thoughts are to actually probably have some sort of mechanism to actually authorize validators, including their slashing or maybe restaking kind of mechanism to actually allow them to insert the mempool into the centralized database, so that the builders can be decentralized and the validators can be much more decentralized, and everybody can actually pull the data from there and start building blocks. But when you just mentioned the state delays, then it came to me where some of the transactions in the mempool might already be confirmed and some might not have it have it in their blocks, some might not have it in their blocks. And do you have any way that I could actually manage this, or any kind of additional data that I could manage this?
That's a very complicated question, because I don't really know your system, right? But in general, so usually transactions don't really live in the mempool for long. If you look at Etherscan, you will see that like most of the blocks are not full, and so there's a lot of like most of the transactions will make it into the chain quite quickly. There are only very few transactions that are not staying in the mempool for longer time, and these transactions that are staying in the mempool for a long time, and these transactions are staying in the mempool for a long time because of two things. They don't pay enough for the base fee, or if they pay enough for the base fee, then they are not valuable enough to be included by builders. So you really only need to be a profitable builder, or to be someone like a builder that actually makes any sense. You only need to take care of these. You only need to focus on the transactions that are really at the tip of the chain. Your kind of system does sound interesting, because the transactions that are executable pay enough and stay in the mempool for the long time. Those are transactions that are being censored. So basically, what you've built, if you notice it or not, is basically a database of censored transactions, and that is something that we need to build anyway for Fossil, because we want validators to be able to specify a number of transactions to the builders to say, hey, I'm the validator. I'm going to produce the next block, and I want you. I'm going to sign the next block, and I want you to produce a block for me that includes those transactions, or you have to produce a block for me that includes those transactions. And then the builder has no cannot do anything else but to mine those transactions. And so what you've been building is kind of a database for solo validators to see sensor transactions on the network. But you will always have the problem that most of the transactions that you're recording are going to be included in the next block, and only a very few will live longer. And so and also everyone has to create these databases by themselves. Otherwise, it would be kind of centralized, and it would defeat the purpose of Fossil. But if you're interested in like solving, like playing around with these transactions and solving the kind of the censorship problem, then I would encourage you to look into Fossil. I will write it into the chat how it's spelled, Fossil. Okay, I cannot write anything into the chat. Anyway, it's Focil. Other questions?
So I got a question for you real quick before we wrap up.
Yeah, shoot.
So we have Fusaka coming up, F star in Osaka, and then we have G star in Amsterdam, and then H star in Bogota after that, and then finally I star in Istanbul. But there's already been an Istanbul fork.
Yes.
So what are we gonna do about that?
I have no idea. Probably we're just going to find another name for Istanbul.
Like Constantinople?
Or Byzantium, or like previously, I don't know.
Forks.
Yeah, most people are probably not aware, but a lot of forks were actually in the beginning. Most of the forks were other names for Istanbul, like historical names for Istanbul, and that of course, like, we had to make much more forks than there were names for Istanbul. So if the Istanbul fork comes up, then we kind of don't. Probably we'll just skip it, or we'll call it Istanbul 2 or something.
Great.
But
all right.
We still have some time for that.
We do. Probably a few years.
All right. I hope you guys liked it. I hope you guys could take something away from this. And as I said, I'm always trying to be like close to the community. Try to help people out. So if you ever want to just, I don't know, whatever, chat, you can find me, hit me up, and we can talk about cool stuff on Ethereum.
Thank you. I found the site, FOCIL.
Yes.
It's an EIP. Thank you very much.
Cool.
Perfect. Thank you very much, Marius. And thank you, everyone, for being with us here till the very last session of the study group. Amazing. Yeah. So, thanks a lot again, everyone. Marius, especially, it was really great. Great insight there. We learned a lot once again. But we need to wrap it up here. So the original plan was that Marius will have a short talk, and we are like 1 hour over what we planned already. So we wanted to do some extra session for like the study group wrap up, office hours, feedback, and so on. But we will do that in a separate session. So this is more of an organizational thing. This is not our last call. It's our last lecture, but we will have one more call for the study group attendees to chat with us, to somehow reflect on the study group experience. And also we will have some announcements there. So stay tuned. We will announce another call in the Discord soon. But for now, it's over, and it's been a great ride with all of you. And I hope you enjoyed. I hope you learned a lot. We will chat about it more next week. And again, thanks, Marius, for a great finish to our 2 months of protocol learning. Yeah.
Thank you so much, Mario, and also thank you to you and Josh for organizing the study group, which I think was I only heard good things about it. So yeah, thank you for doing the organization and for making everyone interested in the protocol. And if you are still interested in the protocol, then also join ETF. Yes, sir.
Awesome. Thank you so much for the shout out there, Marius. That was great. Awesome. Yeah. Yeah, very well. So I think that's it, guys. It's been the last lecture, and we'll please keep an eye on the Discord. We will